Hello, everyone. This is lesson 5 for verifying trigonometric identities. So the first thing we're going to look at is we've already looked at the Pythagorean identity, but actually there's 8 versions that we can do. So first of all, let me show you 2 other versions and then we'll manipulate those. So if we start with the Pythagorean identity here of cosine squared theta plus sine squared theta, and I assume that cosine theta does not equal 0, I can divide each term by cosine squared. Cosine squared, cosine squared, cosine squared. And if you see, cosine squared over cosine squared is 1 plus sine squared over cosine squared. Well, sine over cosine is tangent, and since we're squaring those, we get tangent squared. And 1 over cosine is secant, but 1 over cosine squared would be secant squared. Don't forget the reciprocal. So there we have another Pythagorean identity, but we're using tangent and secant. So what happens if maybe we take our Pythagorean identity here and we say that sine of theta cannot equal 0? Then let's divide each term by sine. Now, of course, you guys understand why I'm saying the cosine theta or sine theta cannot equal 0, because of course, since I'm dividing, I cannot divide by 0, so that's why it can't equal 0. Okay, cosine squared over sine squared. Well, cosine over sine is cotangent, so we have cotangent theta. Sine squared over sine squared is 1, and 1 over sine is cosecant, but we have it squared, so cosecant squared theta. Okay, I just found 2 more, but that's 1, 2, and that's 3. How are we supposed to make 8 other versions? So 9 altogether. Well, this is where instead of watching me write everything down, I'm going to show you. Okay. So if we look, we have the Pythagorean identity. First of all, we can make an extra 2 just by moving things around. So I can say cosine squared theta equals 1 minus sine squared theta. Same thing as I can say sine squared theta equals 1 minus cosine squared theta. Now I can take what we just learned over here, which of 1 plus tangent squared equals secant squared, and move that stuff around. So tangent squared theta equals secant squared theta minus 1. And I can move the tangent squared over by saying 1 equals secant squared minus tangent squared theta. And then I can do the same thing with my cotangent squared plus 1 equals cosecant squared. Now, why is this worth it? Because we are going to prove other trig identities by using ones we already know exist. So identities play a huge importance in trigonometry and calculus. We're going to use them with our circular functions, and we're going to use them to solve equations. In calculus, though, you're going to need to rewrite and manipulate functions to make sure that you can simplify it and continue whether you're doing derivatives or integration. And you'll find out that later if you haven't taken calc yet, because this is before calc. So what we're going to do is we're going to prove these trig identities by, again, using what we've already known. So it's going to take some time to recognize. I also want you to keep aware that when it's something that seems so simple and you're like, well, yes, that equals, so let me just check it off. We do have to write down every step because we are proving of why these identities exist. So take your time with this. Just remember there's no shortcuts, okay? So here's a couple of things that I highlighted that will help us through it. When you prove things, it's going to be easier to look at the more complicated side and manipulate that side into looking like the other one. Okay, we have to remember to be writing down our reciprocal identity. So if you don't like using cosecant, use 1 over sine, so on and so on. We also have to remember that when we have two rational expressions, we can add them and subtract them by doing common denominator. We can manipulate things into the Pythagorean identities to be able to exchange cosines and sines and cotangent and cosecant, so on and so forth. We can multiply by conjugates to take advantage of the Pythagorean identities. Again, we're going to do a couple of these so you can see what happens, okay? Then if you get stuck by doing both sides, maybe go on to the next side to see if you can manipulate the other side to make it look together. But really try to keep going with manipulating one side, okay? And keep in mind, this is very, very important. We're not solving, okay? So you can't move one side to another. Okay, if you see multiplication on the right side, you can't divide both sides by that thing and blah, blah, blah. We are not solving. We're making one side look like the other to show you that they are equal. Okay, so A, we are actually proving a reciprocal almost by using the reciprocal. It's kind of weird, but watch. So the first thing I'm going to do is I'm going to look at this and say, hey, I think the left side looks a little bit more complicated. So I'm going to rework the left side to make it look like the right. So I know that cosecant is 1 over sine. Okay, now I'm not going to write down the side that I'm not manipulating down, and I'll just check it at the end. Well, 1 over sine. Well, dividing by a fraction is the same thing as multiplying by the reciprocal. So then we manipulate that to sine theta equals, and of course we got our other side. So I usually just check it off and say, look, I got there. Now B here, if you look, what side is more complicated? I would say the right side. So let's see what we can do. Well, I don't like the secant there, so I can change secant into 1 over cosine theta. And then I can actually multiply that out and get sine theta over cosine theta. And then what do I know? Sine theta over cosine theta is tangent theta. Check it off. Another one. Okay, more complicated side, of course, is the left side. So the first thing I'm going to do is multiply these binomials out. Now, if for some reason you think, hey, I just don't want to be missing a step, then write down what the step is. But right here, I'm going to multiply this out, or FOIL, depending on what you want to do. So secant times secant is secant squared. Secant times tangent is just a positive secant theta tangent theta. Okay, negative tan times secant is a negative tangent theta secant theta. And negative tangent times positive tangent is a negative tangent squared theta. Okay, now I see that these two cancel, so I'm left with secant squared theta minus tangent squared theta equals 1, and I know from my one of my Pythagorean identities, I get 1 equals 1. Well, I guess I could have checked that out. There we go. Let me do it that way. There we go. Okay, again, knowing that I can identify this step into this by saying Pythagorean identity. Okay, D here. Well, to me, they kind of both look complicated, but I think the left side looks a little bit more complicated because I'm dealing with secants instead of cosines and sines. So the first thing I'm going to do, considering I like cosines and sines, so I'm going to switch the secant to 1 over cosine and switch the tangent to sine over cosine. So 1 over cosine theta all over 1 minus sine over cosine. Okay, now my next move here, I look at this and I'm like, wow, there are too many fractions within fractions. So let me get rid of that. Let me see that the denominator is cosine. So what if I then multiply, and I'm going to leave myself a note so I know what I did, multiply by cosine over cosine. Am I able to do this? Yes, I am, because cosine over cosine is the value of 1. So I'm not really changing anything. When I do that, I end up getting, so this multiplied by the numerator gives me cosine theta over cosine theta all over. Well, if I multiply both of these by cosine theta, I get cosine theta minus cosine theta sine theta all over cosine theta. All right, so what does that do? Well, on top that gives me 1 over, okay, this gives me cosine theta here, minus, and as you can see, both of these cosines cancel. Well, change it to 1, right? Cosine over cosine is 1, leaving sine theta. And look, this is what I wanted my outcome to be, and I'm done. The last two, I'm going to divide this in half so my work doesn't run into each other. Then look at E, what side looks more complicated? Hopefully you said the right one. So I'm going to put my equals and work on that right side. Now, if you look at this, we have two rational expressions that we can put together into one, right? We have to have a common denominator. So what I'm going to do with the common denominator is multiply each of them by each other's denominator. So 3 times 1 plus sine theta minus 3 times 1 minus sine theta. And then, of course, the common denominator means I'm multiplying both by each other. So 1 minus sine theta times 1 plus sine theta. Okay, now let's distribute. Do all that nice stuff. And in my denominator, since I don't have my denominator on the left side is 1, I'm actually going to multiply that out also. So let me distribute for the numerator. So 3 plus 3 sine theta minus 3 plus 3 sine theta. All right, as you can see, guys, these are conjugates. So difference of squares, right? So the middle term cancels. So I end up with 1 minus sine squared theta. Remember, right down here, this is a Pythagorean identity. So on top, the 3's cancel, leaving me with 6 sine theta all over. Well, 1 minus sine squared theta is cosine squared theta. I'm going to break that up into 2 denominators. So I get 6 times 1 over cosine theta times sine theta over cosine theta, right? I'm just breaking that up. And if you see, this is where we get our 6. 1 over cosine is secant theta. And sine over cosine is tangent theta. What do you know? We got our proof. Again, watch your little steps. Anytime you're like, well, I can see that that is that, you need to mark it down. Like, it's tempting to go sine theta over cosine theta and automatically go to your answer. But the truth is sine over cosine squared theta, we don't know is actually this. What we do know is we can split it up and then say 1 over cosine theta is secant theta, or sine over cosine is tangent. All right, F. Well, they both kind of look complicated itself, but if I think of complication, right, I think of, okay, what makes this look ugly? I don't like denominators because I don't like fractions, but what denominator looks worse? My left side, right? So what we're going to do, though, is also, because I do not like that denominator, I'm going to multiply the top and the bottom by the conjugate. Okay, I'm making myself a note so that way I know what's going on. Okay, so the conjugate would be 1 plus cosine theta times sine theta all over 1 plus cosine theta times 1 minus cosine theta. Okay. Now what I'm going to do is on top, I'm going to distribute that. Or actually, you know what? I'm not going to distribute it. This one I distributed. This one I don't want to. Why wouldn't I want to? Well, because I see what I'm trying to make it look like. It's halfway there. Do you guys see that? So I'm actually not going to distribute on the top. I'm going to keep the numerator as 1 plus cosine theta times sine theta. On the bottom, though, I am going to multiply that out because this is, again, difference of two squares type of thing. So the conjugates give me, multiplied together, give me 1 minus cosine squared theta. Because 1 minus cosine squared theta, I think of the Pythagorean identity. So my next line would be 1 plus cosine theta times sine theta. Well, the Pythagorean identity there tells me that's sine squared theta. Again, I know it's so tempting to do the next step and just go straight to the answer, but the reason why I can cancel out is because if I separate the sine squared to sine theta times sine theta, now I can see that those equal 1, and I'm left with 1 plus cosine theta over sine theta. So yes, did I go through these answers ahead of time before a lesson? Yeah. Is it going to take you a moment to realize, should I do common denominator? Should I multiply by the conjugate? Do I use the reciprocal? Is that a Pythagorean identity? Yes, you will have to take time and you will have to struggle through it. It gets better the more you use them, okay? So make sure you're trying to do all your practice work in one situation. Once you get in that flow and you get all those ideas in your head, it makes it easier and faster. But at first, expect to struggle and almost go, I don't know what to do. Stick with your rules like we had on the other page. Manipulate one side. How can you manipulate that one side? So on and so forth. All right, try some on your own.